So far in subtopic 11.3 on capacitance, we've looked at what capacitors are, the fact that they store charge, how they're made, and how we can add them in series or parallel. In this video we're going to have a look in a bit more detail at one of the particular uses of capacitors, and that's using capacitors in timing circuits. And you can see with the title that we're dealing with here, we need to not just use a capacitor but also a resistor. Now, what I mean by a timing circuit is an application where you need something to, say, switch on and off at a particular time, on or off. And so something like a flashing light, for example, you want it to be flashing at a certain rate, and so you can use a capacitor in a more complicated circuit in order to achieve that purpose. We're not going to focus on the full detail of those sort of circuits. We're just going to look at how a capacitor can be used in that sort of timing process. And in order for that to work, the capacitor needs to be connected to a resistor. And the reason for that is that if you think about what we've talked about with capacitance, the time to charge or discharge a capacitor depends on current flow. So the charge time of a capacitor depends on current flow, and discharge likewise. And so if we have a large current flowing, then the capacitor will charge quickly. If we have a small current flowing, then the capacitor will take much longer to charge. And that current flow is going to be affected by resistance. So we know Ohm's law governs the relationship between voltage and current across a resistor. So if we add a resistor to a circuit that has a capacitor in it, we can then change the how long it takes for the capacitor to charge and discharge. Now, we've been talking about charging here. We're actually going to focus on discharging. It's a little bit easier to deal with, and the syllabus itself specifically focuses on discharging in a lot more detail. I'll briefly mention some aspects about charging at the end of this video though. Now, before we get started on the explanation, we'll start off with a very simple circuit that could be used to charge and discharge a capacitor. So first of all, we've got the charging loop. You'll notice in this loop there's no resistance, so the capacitor is going to be able to charge very quickly because a very large current will flow. So that's our capacitance there. We're interested in this potential difference VC, and we'll call this switch 1. Now, we're also going to connect to that a secondary circuit that uses switch S2 in order to discharge the capacitor, but here we're also going to add a resistor R, and that has a potential difference of VR across it. Now, briefly just talking about charging, when S1 is closed, so that would look something like this. So if we were to close that switch across there, very quickly the capacitor will charge up, so the potential difference VC will be equal to that source potential difference, or the EMF that we're using V0 to denote. And when that happens, the capacitor is fully charged. So that's not a particular focus at this point in time, but just mentioning that we first of all need to charge the capacitor. After that, S1 is going to be opened, so we need to make sure that we don't have both S1 and S2 closed at the same time for this explanation. So S1 is opened, then S2 is closed. So we'd then take that switch and we'd close it there. Now, initially, we need to look at this in a few stages. So initially, what we're going to see, because we've charged the capacitor, the potential difference across the resistance is going to be equal to the potential difference across the capacitor. And so that means that initially the potential difference is going to be the source potential difference V0. And as I mentioned earlier, since we know that a resistor is governed by Ohm's law, so we've got the VR is equal to R times I, we've got a potential difference across the resistor, we have a resistance, and so that means that we've got a current that's going to flow. So current flows through the resistor. Now, in this sense, the capacitor here is effectively acting like a power supply. So the charge separation that we've got on the capacitor, it basically means that it's acting like a power supply here. So using the capacitor as a power supply. Once we get that current flowing, we then need to sort of look at the next bit, the next sort of step in the process. The capacitor is going to then discharge as the current starts to flow. So as the capacitor discharges, that means we have less charge on the plates. That means that our potential difference VC is going to decrease. And if VC decreases, so does VR, given that we've only got the single loop and we know that any voltage inputs will be equal to the voltage outputs, thanks to Kirchhoff's law. So VR is going to decrease, and if VR decreases, going back to Ohm's law again, that's going to cause the current to decrease as well. So that means that once we start to discharge, initially it'll be a fairly large current, and so a fairly initially a fairly quick discharge, but then as the discharge continues, that current's going to decrease, and so the discharge rate will also decrease. So there's the second stage. Right at the end of the process, so eventually we're going to see that VC will be equal to 0 volts, and as a result no more current will flow because there's no more separation of charge to redistribute. So there's sort of the 3 stages to think about in discharging the capacitor. If we consider the scenario there graphically, so in order to take this a step further, we'll first of all look at the graphical representation of that, and then we'll turn that into some equations that you'll find in the data booklet. So on the left we're going to have current, given by the symbol I, and time on the horizontal axis, and on the right we'll have the voltage VC, again with time on the horizontal axis. And so both of these graphs might be better to stack them one on top of the other so you can see a little bit more clearly what's happening, but I'll do them side by side just to make it easier to represent on the screen. Now initially we'll have this current that's quite large. We'll denote that as I0. So when the switch is closed, so at time t equals 0 when the switch is closed, we've got a large current. Eventually it decreases and we'll sort of start to plateau or form an asymptote on the horizontal axis. Likewise with the voltage V0, we'll see the same thing. I should mention this is across the capacitor. We'll see the same thing happen with the discharge of the capacitor, and the voltage will decrease that way as well. Now, because we know that it's going to take longer and longer to get completely discharged, we can see there that in both graphs we've got horizontal asymptotes. And the horizontal asymptotes basically mean it's going to be difficult to determine when it's fully discharged. We're going to use a different quantity instead. So because those asymptotes make it difficult to identify when the capacitor is fully discharged, we're going to use the property of, or not property, we're going to use the time constant instead. So the time constant, as the name suggests, is a time that is constant for a particular circuit. And the symbol for time constant is the Greek letter tau. Sort of looks like pi with only one leg to it, and that's the time constant is stated instead. Sorry, I don't need those words. So the time constant is the time taken. Sorry, time. Or the time for the capacitor to discharge by 63%. Yeah, you might sort of think, well, why are we talking about discharging by 63%? Keep in mind we're sort of not really looking at the charging time, but ultimately you could then say that it's the time to charge by 63%. If we're looking at discharge though, we're discharging by 63%. That means it's going to go down to 37%. So the equation for time constant is a pretty straightforward one. It's simply just the resistance multiplied by the capacitance. That is in the data booklet. Now, if you go through, and we might do this in class, if we go through and look at R times C and the units that are involved there, we can actually show that R times C is a time, and this is the reason why we use time constant being 63%, because it comes out nice and easily that corresponds to the resistance times the capacitance, or it's defined by the resistance and the capacitance. Now you'll notice here that the time constant will increase if we increase the resistance. Likewise, it'll increase if we increase the capacitance. So either of those two quantities can cause the time constant to be longer. Going back to those graphs, you'll notice that they resemble a type of relationship that we've already seen before. So this is now where we're going to have a look at the mathematical representation rather than just the graphical representation, and it's an example of exponential decay. So the other situation where we've seen that is with radioactive decay, which was governed by an exponential decay relationship. Now, we don't need to go through the derivation for these to show how they all come about. What we can state though is that the current is going to be equal to the initial current multiplied by the term e to the negative t on the time constant tau. So that equation governs that shape where we start off at I naught and then it decreases over time. Similarly, the potential difference across the capacitor is given by V naught e to the negative t over tau. And I'll mention this one as well, only because it's in the data booklet. We can then sort of look at the fact that if the current is decreasing, that then means that the charge that's stored on the capacitor also has to decrease. So that will be given by Q naught e to the negative t on tau as well. So all those quantities mean the usual things, so I'm not going to bother talking about those. All three of these equations though are in the data booklet. We'll have a look at a few problems in class that relate to these so that you're familiar with making use of them. Finally, I mentioned earlier that we talked very briefly about charging. The syllabus actually identifies that we don't need to do charging in a mathematical sense, so we don't need to look at those equations. All we need to do is consider what's happening graphically. So if I quickly sketch these graphs again, so current and voltage graphs. If you think about what's happening with charging, probably makes more sense to talk about the voltage first, given that we know that charge separation, or as the charge separation increases, the potential difference will also increase. It will increase up to a point of the source that we're provided with, or providing the potential difference. But we know that across the capacitor initially it'll be zero because there's no charge separation. So we actually see a graph that looks like this instead. So basically the discharging curve, but flipped, where it has an asymptote at the supply voltage V naught. Now if you think about the current that's flowing, if you start charging a capacitor, initially a large current is going to flow, and then the longer that it takes to charge, the less current that's going to flow, because we've now got more and more charge and it's harder to add more charge onto the plates of the capacitor. So the graph for charging for current is the same, so it doesn't look any different to the discharging for the current. So the only difference there is the voltage really. where the voltage is increasing rather than decreasing. As I said, we'll have a look at some problems in class. We'll also do a couple of activities. We'll either use the simulation or actually grab out some capacitors and resistors and look at measuring the time constant for some fairly simple circuits.